Okay, so we've talked about state machines. We're going to talk more about state machines. Right, the general idea of a state machine is we have a state that has given outputs at a certain time, and given an input, we change states. The two different types of state machines, we have a mealy state machine and a more state machine. A more state machine generates outputs only dependent upon the state. A mealy state machine generates outputs on the state and the current input. So the difference in drawing, right? So we have state diagrams where if I want to talk about the transitions of something, I might have a state diagram like so. I won't always write this where we start. I always assume we start at 0 or idle or something like that. And then what this is saying to us is I have 3 states, and if I'm in state 0 and I see a B, I go to this state. If I see a B bar, I go to this state. These are evaluated each clock period, right? If I'm in this state and I see a B, I stay in that state. That's all this diagram is telling us. Right now, we don't have any outputs. If I had a more state machine and I wanted output Z, right? I could generate these outputs inside of my state. What this means is that if I'm in state 0, I assert or set to 1 Z0. I don't have to write Z0 bar in each of these states. I can, but I don't need to. It's implied. I only assert where it is. That is a more state machine because my output only depends upon the current state. Doesn't care. Regardless if my output is B or B bar, I output Z0 in that state. Now, if I do this, this is a mealy state machine. Because this says if I was in 0, I got a B, I assert Z0 and go to state 2. This is a mealy. To be entirely complete, I would have to go through and say no output for each of those. I'm not going to be too big of a stickler on that, but that's what this is showing. Okay, so we've kind of started talking about in our project, well, in the lab, about when we have like a garage door opener, and we have outputs that are, inputs that are coming from outside of the system, and how we can kind of end up with these not quite stable states, right? Because we need to have the input based upon, we need the inputs synchronized to our clock. We don't like what we call asynchronous inputs. So asynchronous inputs can cause us problems, as we've kind of mentioned in lab 9, I think it is, that we're working on, right? So let's talk about some of the issues and where they come from and some of the ways that we solve asynchronous input issues. So in this state diagram, my logic that gets implemented when I build this, right? So I've talked about this before. I've done a video on it that should be very helpful, where what you're really building in a state machine is essentially some series of DQ flip-flops, right? This is not necessarily just one. It might have, in this case, it's a 2-bit register, is what we would call it, because I need 2 bits to store my state. These bits feed back around into some sort of combinational logic where the output is the state that I'm currently in. The input is the state that will come next as soon as a clock hits, right? So we make this next state, well, watch the video. The video will go through pretty quickly on how you would build that next state logic. Now, I'm going to skip ahead, and rather than generating that here again, this next state is pretty simple in that sorry, screw that up real quick. Let's call out the bits one at a time, so D0 and D1, right? So it turns out that D0 only matters on B. Now, we would generate that by just going through some K-maps of this. But that's what the video that I keep mentioning is about, is generating those K-maps, generating the logic. But you can kind of see that. So D0 here, if I get B, let's make sure if that happens. If I'm in 0, 0, and I see B, get 0. If I'm in 1, 0, and I get B, I still have 0. B bar, 0. Not quite sold on this one. B bar. I almost feel like that should be not B. I'll have to go back and look at that, but
Isn't B the most significant?
no, B is the input. This guy.
Yes.
And D0, is it, did they do it that way? That would be awful. 0, B, B is still 1, B bar, oh my gosh. Okay, thanks for calling that out. They're doing D0. Oh, no, I'm just dumb. Haha. D1, D0. There we go. Okay. Then B comes into this gate. And then Q0. So. There we go. So that's all the next state logic ends up being for this guy. But we can have an issue that this state machine, even though we've only written 3 states, has the possibility of going into state 1, 1. Just as possible, right? We would have to have some sort of error here for that to be true. We have to ask ourselves, is that possible? And it turns out it actually is. So if the state machine is in 0 and B asserts just before a clock pulse, right? So our clock is ticking along and B does something, B is 0, and we do something, so there's a clock, and we start this transition just before this happens, right? D1 might change immediately, and D0, right, because B is here, so B gets passed to D1 with no delay. But B gets passed to D0 with a delay. So D1 goes, oh, I'm supposed to be a 1 because we're going to 1, 0, right? I've got B, I'm going to 1, 0. I'll say that one more time just so we do. I'm in 0, 0. The clock hits, or a clock hits at the same time I'm making this transition, right? So without any delay, essentially, because B is already there, D1 goes, oh, look, I need to go to 1.
but there's a delay. So D0 doesn't yet know that B has changed. So, oh, sorry. So here, I guess we're okay. Is that true? Nope. Nope. So because of this input will change, that will toggle with the delay. And we can accidentally, therefore, if that happens, slide into 1, 1. Because B has changed, has updated this faster than this can update. We have a little bit of a delay, and suddenly now we're in a bad state. What does that do if I'm in state 1, 1? We don't really know, right? Because the logic is treated essentially like don't care for those 1, 1 states. So depending how we implemented those don't cares, we may get stuck in that state forever. We may bounce out of it to some other state. We don't know. Which is obviously a problem. So we talked earlier, I feel like forever ago, about some of the rules for creating these states, the numbering, right? Because as long as you follow the rules, you are less likely to end up in erroneous states. Essentially, the more ones and zeros that change between states that are adjacent, that are connected, the more likely you are to run into a problem. Because there are more different combinations of delay paths that might cause you an issue. So that's why those rules that we talked about before are helpful, is because we want to make sure we minimize this risk. But what if we want to move towards, say, eliminating this risk? Well, the best way to eliminate it is to never use an asynchronous input. It's just make sure that my input only ever asserts based on the clock, right? So if my changes only ever happen here, sorry, I'm fine, right? Because I only worry about the rising edges. If I never change near a rising edge, I can't end up in an erroneous state. So what we want to do is synchronize our inputs. Well, if all we do to B is add just a simple DQ flip-flop to it, is now the output here can only change on the clock. Therefore, this input is synchronous. B is not synchronous, this is synchronous, right? Does everyone follow that? Now, there is still one potential problem. It is possible that B changes at the same time as this clock, and then the output enters what we call, if you recall from the debouncing section, metastable. Is that it has to be 1 or 0, but we don't necessarily know what it is, right? The analogy of the coin balance on edge, is this going to fall one way or another once it's settled, but we don't know where that goes? How do we solve the metastable issue? Just like debouncing, we add a second flip-flop. Now, it's still technically possible for this to go metastable. So this goes metastable, and it's possible that this doesn't resolve in time and we end up metastable here. But as the book puts it, what did they say? It's more likely that the device will be struck by lightning than for that to happen.
Is the clock here on the big? Is the clock the same as the other?
Yeah. So, but solved, right? We now have a synchronous input regardless of what B is doing. We might get we have a little bit of delay from B, They're not really an issue.
Can we do that for the lab?
Sure, why not? Okay, and in fact, we're gonna get to another part that I had forgotten that this exists. So this is actually really good that I came back to this book at this point because this will be really helpful. Is, let's say, like our lab, that we want to indicate an event. We want to raise the clock for only one clock period, right? So just like our situation with the garage door, where I push the button and I don't necessarily want to toggle the door a whole bunch of times on every clock. So each time I push it, I just want to send one pulse for one clock, right? So during lab, I came up with a rather convoluted way of doing this. It turns out, and I forgot this, there's an easier way. And this is where education comes into play. And I don't mind admitting, I don't know everything with digital design. There's still things that I learn and I've probably forgotten more than you guys know yet. And that's not really a problem. So we will create what is called a single pulsar. It just pulses once when we change it, but it doesn't stay there if I hold it. Saves us some grief in our current lab. Well, as with everything wonderful in this world, it starts with a DQ flip-flop. In fact, it takes 2 DQ flip-flops, which probably surprises nobody. So they're saying here's a key 1. This would be key 2. And this is key 2 bar. And of course, I don't always draw the clocks right, but they're kind of inferred.
So the press, you have a AND gate, the press is like that would be the same.
That would be the pulsed output. So what I want is the key is a slow signal compared to these D flip-flops. I only want this to assert for 1 clock cycle when I change key, right? So let's look at, I drew myself into a corner here, guys. All right, let's look at some timing diagrams. So key, it's gonna come along, it's gonna go high, it's gonna stay high for a long while, and then it's gonna come back low. Key 1, well, it needs a clock that's pulsing along at like, let me see about roughly what they're doing. It's changing just so. Okay, so this, let's say, just makes it inside after that clock. So it goes, aha, it's been changed. So what that means is key 1 says, oh, look, something got clocked in, so I'm gonna change, right? There's a little bit of delay between key and key 1 because key 1 doesn't update until a clock happens and key is high. So just a little bit of delay, not really a problem. And it's gonna stay high until the clock cycle after that goes low, right? Because again, it can't update until that. But with only that DQ flip-flop, we've just added an offset. We haven't really fixed the issue, right? We still have a long pulse. Well, let's look at key 2 bar. Well, what it's going to do is it's going to start out the opposite of this, right? Because key was getting past a key 1, was getting past a key 2. This is key 2 bar. So it starts high. Well, nothing can happen yet because it's a whole clock cycle behind. So we have to wait until this clock cycle where key 2 or key 1 is now updated before I can even start to do anything. Right? So then we lower because that's happened. Key 2 then stays low until a clock cycle after Q1 changes, right? Well, now let's look at this logic, the AND, where I have AND of key 1 and key 2. Where does that happen? Here, and only there, for exactly 1 clock cycle.
But it's more on the racing. You say it on the land, it will be better if you come.
Yeah, so I will get there. So then press right is low. It goes high. And then, shoot, am I off by this on 1? High. No, that's okay. Okay. And it might be shifted a little bit because there's like a little bit of delay to the AND gate. Okay, so what you've pointed out is absolutely correct. We now have an issue where we're never really high, except for in situations where there's going to be a little bit of a race condition, right? But what happens if this whole thing, say the input to this is not clock instead of clock, right? Then if the rest of the system is built on clock and this is built on not clock, then what does clock look like? Well, here, clock is a falling edge. Here, clock is a rising edge. There, clock is a falling edge. Right? Because this is clock. That's not clock. So now our rising edge happens right in the middle of that bit, and everything is happy.
Can you give an example of the ACE?
Let me see if I get to that or if I.
Would we build this like, would we build 2 DQ flip-flops, or how would we do it?
How do you build a DQ flip-flop in VHDL? Okay, yeah, we got multiple people with the same issue, and it doesn't look like I get to it soon.
Or can you just do like, can you do it like a state machine? Be like, if P1 is high, I guess.
So yes, you could, but it's actually easier than that. Is we'll just create a signal. So let's take a process that takes the or a module that takes the inputs of clock and key, outputs press, right? So then I would just create a signal, I don't know, clock internal, which is equal to not clock. And then I want to create a signal, key 1, is equal to key, and key 2 bar is equal to not key 1. And when I do this type of statement, all I'm really doing is storing a value, right, in a flip-flop.
All that under a if writing itself.
Yes. Yeah. And technically, just to be safe, we should technically put this one above if we're inside of a process. I think. Maybe not. No, this is probably okay. Well, I'll have to do some testing and thinking about it. I haven't thought that far ahead yet. So key gets written in, key 1 will already be updated when I execute here, and do I really want that? I'll have to think about that. I think it has to be above in order to work correctly in the process. Best to run a simulation just to make sure. Anytime you're not sure, because I'm not sure right now, I have to think about that. But yeah, a state machine works too. Works really well, in fact, because the thing that is nice about state machines is they're clear and obvious what they do. And the nice thing is all of this issue that we kind of talked about with the jumping to erroneous states, the synthesizer works really hard on our behalf in order to prevent it from going to weird states. We can ensure that when we write the VHDL for a state, right? And we've talked about that. You do case, blah, 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 when, blah, 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 when, blah, blah, blah. And then the others, you can, at the bottom, you can write others and tell it what to do when others. So you say when others, go back to idle, right? So if something does happen, we go back to whatever our idle state is. Now, in the case of the garage door opener, we don't have an obvious idle state necessarily. The one that I would set as my idle in the garage door is going down, right? So if something weird happens, it just closes. Isn't that what you'd want to have happen in your garage door? If something weird happened, just close the garage door. Well, yeah, but it still has the sensor that tells if there's something in the way of it. And yeah, there's a, you might need to like build up a more complicated system that says like if jammed kind of question, you know?
Mine seems to have idle state going up. Not idle state, I guess, but
The default, yeah, so. Yeah, so that, I mean, that might be fine, right? Maybe the correct state to go to is ready to go down or ready to go up. Because that's kind of an idle state, is it just sitting there going, I don't know. But the point is, the benefit in our state machine of the ready to, or the going down, is that after a short while, you'll end up in a known state. But if you're ready to go up, that's not really a problem either, as you kind of point out. It might be better.
from the safety
Yeah,
side.
I've never had a garage door, so you know I grew up with carports, so I've never been to one of these rich fancy people with garage doors. Yeah, but no, it's a valid point. That's fine. Okay. So there's another type of issue that we can run into that we've alluded to, right? So do you guys remember we talked about hazards, right? Do you remember?
Hazards?
Did we talk about hazards?
Don't remember, but
Maybe we didn't. Man, it's been a long semester and I mix up the two. Okay, well, let's talk about what we call glitches. Glitches and hazards are very similar issues. So let's say we have a little bit more complicated of a state machine. Okay. So this is a state machine that they've provided for us as an example, right? We can kind of follow what happened. If we're in state 0, we see B bar, we go here. No matter what, we go here, and then no matter what, we go back to 0, 0, right? There's no options. That just happens. Here, if I get B, I go here, evaluate on B or B bar, and then go back. Now, there is a potential issue. So they assure us that they've designed this to the rules in, I forget the chapter, a previous chapter that talks about assigning these codes. But it's a complicated state machine. They weren't quite able to follow all of them. Now you'll notice there is a little bit of a risk of something weird going on, because here to here, we are literally flipping every single bit, right? And we don't want to end up in a situation where we have, like what we talked about earlier, where it ends up in an undefined state or ends up temporarily in the wrong state. And it might be temporary. But let's look at the logic that gets implemented here if we build this. And I'm just kind of skip to it to illustrate the logic of it. We could build this up. It wouldn't be too bad because it's got one input and three bits for the states. So it's only 4 bits that we have to worry about in the next state logic. But we end up with the book provides these as dot lows. I'm just going to write them as bars. I like it better. This logic. Okay, so let's look at the output here. When we transition from 101 to 010, we can end up with a bit of an issue because we have we have different delay paths for bits that are all changing, right? If we only change one bit in its delay path, we're probably okay. But because we're changing Q1 and Q2, and they have different paths, we can have an issue. Because the output can change faster as a result of Q2 than it can change as a result of Q1 and Q0. So we're going to start out at 1, 0, 1 for those inputs. We're going to move to 0, 1, 0. Okay, so at this state, we want to have the output of this gate. Let's follow through at the beginning, right? So Q naught, we would have 1 and 1 because it's Q naught. And the input and output would go to a 1, but that would be a 0. Starts as a 0. So we have a 0 Q bar is Q2 starts as a 1. but it goes to 0 because we're Q2 bar. So we have a 0 at this input and a 0 at that output to start. Or sorry, 0 at this input, 0 at that input. What is our output in that case? Okay. Now, we're going to change to 0, 1, 0. Okay, so if I have a 0 here and a 1 here, this transitions to what? So 1, right? Because we have not here. So we have we're gonna have a 0 at this input, a 0 at that input, because it's inverted. 0, 0, 1. Okay, Q2, 1 to 0, 0 inverts, we go to 1. 0 to 1, 0 to 1. What do we end up here? Is it still 1?
Yeah. Whenever there's one period, it should pop.
Yeah, if it's not a 1, I screwed up somewhere, which is not impossible. I'm not perfect, right? But that seems right. We could draw the truth table for the the Nand gate if we wanted, right? So that is just a Nand gate. All right. So theoretically, the output shouldn't change. But if this guy has a 5 nanosecond delay and that guy has a 5 nanosecond delay, this goes to, and actually, you know what? Let's go ahead and write up the Nand gate truth table just real quick so that we can not screw this up. So an AND should be that is a NAND gate, right? Yeah. And a NAND but so shouldn't this go to a 0 then if we got 0 and 0? Because we got a 1 here and a 1 here.
But they turned into one. Problem inside is the bubble. They were coming in as a 0.
Well, let's look at these in this state that they're in. Where this one should be a 0 to a 1. And Q2 goes. I think this is where I screwed up actually. So normally I have a 1 and a 0 at the input, which means I have a 1 and a 1. This is 0. Sorry, I feel like I screwed something up here and I'm trying to puzzle out which one it is. Because this is correct. I'm trying to get to a state where I stay 1 to 1. There are situations in which case I can stay 1, but have a temporary blip. So maybe I just need to draw this out as a timing diagram, which is, I was avoiding that until the end. Where we're going to change here, Q2 bar is Q2. We're going from 1 to 0. but Q2 bar is going 0 to 1. Then Q1 and Q0 bar is going to do low, and then it's going to have some delay. And let's say that delay happens here. So Q2 changes. Oh my gosh. Oh no, Q1 changes. Everything changes here. And that means that Q1, Q2 changes. Sorry, these timing diagrams get really annoying, so I'm a little bit slow here. But we'll make you do lots of these and you'll get better at them than I am eventually. Okay, right? So we're gonna say this is the moment that we change states. So Q1, Q0, and Q2 all change right here. It takes one delay, we'll call it 5 nanoseconds, in order for this signal to change as a result. Okay? Then it takes this one, they're calling it glitch, we'll just write G, which starts as 1. Because we're 0, 0, our output is 1. Here, 0, 1, 0, but we just see that happen here, so we need to wait a delay, right? And then we can evaluate what is 1 and 0 in our NAND gate. 1 and 0 is 1, which is why I'm going crazy. Because they're showing me one delay. So change, they're showing that I should get this. And I can't help but think that the issue is a book typo with a bar somewhere, because that happens a lot, right? And I don't think
Oh, Q1 would be, so in the book, it looks like it starts at 1 all the way through. On the Q1, Q0.
Oh, okay.
And then it drops right at that second spot.
Oh, so they're doing this, which is a dot low.
Yes.
It has to delay here, there.
Yeah.
And
So
so,
it's misreading it as a 0 for a 1, 0. No.
yeah. Man, this is a really awful example, or I'm really dumb today. So, 0, 1. Outputs a 1. A 1, 1 outputs a 0. And a 1, 0 outputs a 1.
Okay.
Yeah. Sorry, guys. Something weird happened here, and I got to figure out what that was. So, if I have at the beginning a 1 on this line, a 0 on that line, 1, 0 outputs a 0, right? So a 0 is on this wire, but they're saying it starts out at a 1 on the plot.
Yeah. Oh, right, because, 1 and a 0 would output a 0, but it's, not, so it becomes 1.
But that accounts for the not.
It does?
Mine, as far as I can tell, right?
Yeah, because it's a low, huh? I don't know.
If you look at the table, 1, 0 is also on the map.
1, 0 is a 1. 1, 0, oh, is a 1.
Yeah,
So we are 1 here.
yeah.
And we're transitioning to 0. There we go. And here we're transitioning 0 to 1. This is why I don't use the dot low notation, is it screws me up really
Yeah,
bad.
that's what's in my head.
Okay, so now that we have the numbers correct, let's walk back over through this so that we can unconfuse all of you. Who's horribly confused? Okay, great. So the main thing here is when we have an issue where there are different propagation delays, we may end up with what we call a glitch. This glitch is coming from the fact that in the start state 1, 0, 1, the output is 1. At the end state of 0, 1, 0, the output is 1. The difference is the 1 is coming from 2 different routes, right? So in order for this to be 1, I need at least one of these to be 0. In the beginning, that 0 is coming from this route.
Oh, okay.
But it goes away really quickly because there's no delay. So because this route stops creating a 0 stop creating the output for us, the output drops. A little time later, we can finally pass this through and get back to the one we desired. But because they come through 2 different paths, we can have a moment in time where the output isn't what we think it is. And if we have something that's looking for, say, a rising edge or even just a change in this output, we have an issue, right? Because we go, oh, look, it changed, let's do something. But it wasn't supposed to change. Let's start this an easier way. Let's do another one of these because I don't want to leave anybody behind. And this is something that even my 3610 students struggled with, and supposedly they had learned it in this class, and it doesn't stick. And timing is really important, and it's really confusing. I mean, you guys just watch me struggle up here. Don't be embarrassed if you struggle, because it can be difficult to walk through the timing. I kind of sabotage myself by not starting with the timing diagram. It is very helpful, but I also sabotage myself by using the book because I don't like the dot low signals and it insists on it. You'll also notice that the book really likes the variable entered maps for this. Again, I'm not really a fan. So let's do one without. Let's create some logic. So let's say I have some next state logic that just simply has state 1, state 0, and what, they're using input as B? Sure, why not? This example is not in the book. Let's just walk through it though, right? So this could be the next state logic for one of our bits. Now, do we remember K-maps? So what we would like to do, if we're creating minimum logic, is that, right? So I have 2 implicants. Remember that word? What does this logic end up looking like? I have 2 AND gates. outputting into an OR. Well, this is fortunate because it doesn't look like I have any issue for 2 different delay paths, right? All of my delay paths are fine. This is good. Let's create one. That's really funny. I need to.
You do like 2 and then 1 by itself.
No, I want to go the opposite direction, I think. Because if I do that, I just get a bigger AND gate unless I'm limited to 2 input AND gates. So I really want one that is just the term. Right? Because then I have one that the only thing that doesn't change here is B bar. And then I have one, then I need another implicant that is something like, actually, this is a fine idea. This is a little bit forced because hopefully you wouldn't do it this way anyways. But let's say we had that, okay, as our implicant. So now I have B bar here and B and S1, right? So this is our output logic. This is our function F. What we want to do is something called sensitizing the inputs or sensitizing the path. What that means is making it so that we can actually affect a change. So if I wanted to test if B has a problem and S1 was 0, could I test B? No, right? So I know that if I want to test B, S1 has to be 1. Because if it's not 1, B will have no effect on the output of the circuit. There are 2 different types of issues that we can have. Here, I don't have any combinational logic, or sorry, any sequential logic plugged in. So this, I'm going to start referring to as hazards. A hazard, we can either, you'll see a couple ways of saying it, but you'll see 0 hazard or 1 hazard. And the general idea is that when I'm going from 1 to 1 or 0 to 0, I may have a problem if there are 2 different paths, if there are delays, right? In order to be able to test B, to see if B has an issue, I need to sensitize the path, which means make it so that just changing B can affect the output. So let's start by testing ones. Let's see if there's a problem with the ones. So in my timing diagram, I'm going to start out and saying I need to consider a couple of inputs. I have B, S1 is fixed, B bar is just the opposite of B, and this signal we'll just call X at the moment. So let's say B starts at, well, I want something that makes F1. So if B is 1, B bar is 0, and we're in good shape. So B is 1, so this is our start point. X then, because B is 1, S1 is 1, X is 1. F then is also 1, right? Okay, next we can move on and say that I want to transition B from 1 to 0. Well, X then needs to wait 1 delay, whatever that long is. I might specify in the question, right? Let's say it's 5 nanoseconds. So B comes along and says, oh, look, it's changed. I need to change because now I went from 1 to 0. This one went 1 to 0. And then F goes and says, well, at this point, I have a 1, 0. This point, I have a 0, 0. Shoot, I need to draw the B bar to make sure I don't screw this up. B bar has no delay. On forever. Then F responds to starts high, goes low, goes high. I think this one is actually going to be fine, right? Because at this moment, I've got 0 and 1 as my inputs to the OR gate. So it's high. And then it has to propagate through. So the next clock cycle, it stays high because it's got 1 gate delay. Then if look at B and B bar, we've got 1 and 1, we're still good. And then here I've got low, but I'm high, so I'm still high. Okay, so our 1 to 1 is fine. Let's check if our 0 to 0 is fine. Same issue. So I'll start a new line. I have B, X, B bar, F. B starts low, goes high. B bar does the opposite of this with no delay. X starts out at, oh my gosh, you know what I may have done stupidly? Oh, well, this is fine. Okay. So X, if I'm starting at 0 on B, X starts at 0, right? And then it can't change at this initial delay because it has to go through 1 gate delay. So nothing can happen for 1 gate delay. And then I need to evaluate, well, B went high, so I go high, and I stay high. So what does F do? Well, F starts at 1 because I have B bar. I have to wait for a gate delay. But then here, X is 0, B is 0. Wait, shoot. Is F supposed to be at 1 here? Double check. B bar is 1. Ah, yes, this is fine. So B bar is 1, right? So that since B bar is 1, F is 1. Then we drop here with a delay 0, X is 0. Neither one of those is true. F drops to 0. Then X bar goes high, creating that 1 back. There we go. We found our hazard. Now, the next step is we want to eliminate this hazard in our circuit. Hazards are bad. How do we eliminate the hazard? Yeah, one way is to make sure that they all have the same delay paths. Another way to ensure that is true, in fact, we can ensure that either that is true or we have some what we would call predictive logic that looks ahead in order to prime the circuit to prevent this glitch from doing something. Now, it turns out we don't have to learn anything complicated or any crazy mathematics. All you have to do is look at the K-map. If in a K-map you have adjacent minterms that do not share an implicant, you have a static 1 hazard. Meaning that you might get this little glitch here when you're going from 1 and staying in 1. What all that means is, if I share the implicant, there is no chance of that happening. So, in a larger K-map, and I won't go through all of this, but right, we may be tempted to just circle this one and that one, because that is our minimum logic, right? But it has the potential for a static 1 hazard. In order to eliminate that hazard, I just add an implicant. It's as simple as that. Now, it is highly likely in an exam, I'm going to give you a circuit, and I'm going to ask you to identify the hazard, which will involve drawing out a timing diagram like I have done here. I would say there's like a 99% chance that I assign a question very similar to this. So, you saw the kind of pain and confusion that could create in you if you just try and think, oh, I know what it is, right? Don't do that. Do this. And you may have to draw several, right? So the first time that I did it, I was like, well, I really suspect I know what the error is. So let's test it. Oh, I got it wrong, so it must be the other one, right? But you need to make sure that you can prime the path. What that really means is if you're not changing a variable, you need to set it to the correct state. In the case of an AND gate, that means set all unchanged variables to 1, so that your changing variable can actually change the output of that. If there was an OR gate that I was trying to prime, what would I set the values to? 0. Because if any of the inputs are 1, it stays a 1 and there's no chance of identifying it. That path is not sensitized. Man, this class went by really quick, didn't it? This is really important information, so it's worth spending time on. Yeah, so that's your main takeaways, is identify what state the inputs need to be in order to sensitize the output so that whatever path you're changing can be changed. So I may be kind to you guys and say, find the static error for signal B. I may not be that kind. But by looking at this, how do you know that B and not S1 is the potential problem? Yes, because B is a signal that has paths of different lengths. S1 only has one place. It can't cause an issue if only one thing is changing. Right? Now, I could ask the question another way where I would do it where we kind of came from on this, where I'd be like, I'm changing from this state to that state. Here's my logic. Find the glitch. In that case, you would just draw out the timing diagram for that transition for each of those signals individually and figure out where the glitch happens. Right? I could give you the stimulus of multiple inputs. Those are the two ways I'm most likely to ask it, is give you what the stimulus is and ask you to show me what the timing looks like, or I will give you a circuit and say, find the hazard. If you're looking for the hazard, multiple paths. If you're sensitizing to test the hazard, AND gates for one, AND gates to ones, OR gates to zeros for the non-tested signals. You may need to think about it in the case of like NAND gates, right? To make sure that you can sensitize a NAND gate or a NOR gate or an XOR gate, right? Let's do it simple. What is an XOR gate? How would I sensitize an XOR gate? What do I set the inputs to that I'm not testing? Zero. On an XOR. Because if one of the inputs is 1, it happens. And you may have an issue with some of these complicated gates. A, B, let's double check this. XOR, right? 0, 0, 0, 1, 1, 1, or 1, 0, 1, 1, 0, 1, 1, 0. So we actually may need to prime this one differently depending on what we're testing. So if A is 0, so let's say I want to test A. So I set B to 0. Then A changing to 1 will change it, right? But there's a little bit of a complication. Yeah. Yeah, so you may need to change the sensitization depending what you're testing on the XOR. So I will probably stick to ORs and ANDs. Just be aware that the way to check the sensitization is draw the truth table of the gate and see if toggling your input from the 0 to the 1 will change it. So here, if I'm going from 0 to 1 and B is 1, I would have a problem. But if I'm doing 0 to 1 and B is 0, it'll change based on that. So 0 is a good one to test that. Right? So just think about it from the perspective of what the gate is doing. I guess we're out of time here. I'll try and do more content on this and assign some homework so that you can work through this kind of stuff, because the timing is interesting. It'll just be the final.
Oh, the final bits.
It should be on the calendar, the schedule. I would double check with the Weber State website. They have like the final scheduling that says like, if your class falls in from here to here, then your final is this day at this time.
Okay.
I would double check, make sure I was correct.
And as of right now, that's going to be in class.
No, it will be.
Oh, like last time. Right?
Like, yes, exactly like the last exam, where you can take it here. Well, actually, I think that one will, everyone will take it remote.
Oh.
I think you'll just take it wherever you are. Yes, there's been a lot of talk about closing down campus after Thanksgiving. So I am not planning on having classes after Thanksgiving. I will have labs if I'm allowed to.
All right.
So usually I have to leave the labs early because I have 4.
Okay.
Which is why I always leave early. But I've been working on lab 9 outside of class. I was wondering if I was doing this like the really hard way, or if I was doing it the right way. Because I got the state machine, sign up. There's 4 inputs, right? So I sign out.
Oh, did you draw out the whole?
I did all of it.
That, oh my goodness gracious. Yes, you did that the hard way.
Thank you. I thought so, but I didn't know what else to do, so.
Yeah, unfortunately, that was the second half of this lecture
Yeah.
that I didn't get to. So I'll keep this rolling for the video so that anyone watching the videos can get this hint on lab 9. Okay, so I did the video for the next state logic, right?
I watched
That shows
that.
you how to do.
Yeah.
Unfortunately, that can give you a bad impression about, oh, I've got this big complicated system.
Right, that's what I was trying to do.
So VHDL and the synthesizer along with it work really hard to keep us from hurting ourselves. All we have to do to create a state machine in VHDL is write a case statement.
Okay.
So I'm sure I talked about this in one of the lectures. I couldn't tell you which one, but it's also in the book. Case statements are pretty straightforward, where I create what's called an enumerated type. Do you remember that?
Is it like a variable or?
It's kind of like a variable where I would say type, I'll call it states. I may get this wrong, is, and I would have something like state 0, state 1, state 2, state 3. Now, what this is saying is I have a new type, just like an integer or something else.
Okay.
And the only things that it can be are these values. And then I go on there and I create a signal, and I'll call it current state, CS. Is of type states. So CS is now a signal that I can use, and it can only be one of those values.
Okay.
Now, I just write case on current state, whatever my current state is, when I'm S0. Then I do stuff. What do I do in state 0? Well, let's say state 0 is going down. Well, going down means I assert the down signal, right? Because this is communicating to a motor. So I say go down.
Okay.
And I also say something like if.
So this is saying when state 0, do you write anything after that assignment indicator there?
No, this.
Or is that all kind of one statement?
So case CS is when S0, and then I'll have another when S1.
Okay, so this is kind of pointing at all of this.
Yes.
Okay.
Yeah. Yeah, and you can do the return even like this. This is pretty close to syntax correct.
Yeah.
This is not.
Right, yeah.
So if the sensor down, I can't remember what they call this input, but if it detects that it is all the way down,
Bottom.
then I'm no longer going down, right? So if this is true, so I've gone, aha, I've detected that I'm all the way down. Then current state is S1, which let's say that is down.
Okay.
So then what happens is the clock happens, it sets down to 1, evaluates if this is true. If it is true, current state ups to S1, and the next time the clock happens, I'm now in S1, and I do whatever S1 is.
So you can write this VHDL straight from the state diagram. You don't have to do any of the.
Yes, exactly. There is no necessary for all this complicated math, comes directly from the state diagram.
Gotcha. That's nice.
For all that extra work, I will happily give you extra credit though.
Oh, I mean, like, I'm glad I don't regret doing it.
Okay.
But at the time, I was like, there's no way I'm gonna do all these K-maps and not
No.
make mistakes.
Yeah.
You know, that was
Yeah.
my worry. Like big mistakes.
Yes.
So.
Yeah, so don't worry. Yeah, I will give you extra credit for that because that was a lot of work. And I like rewarding work, but this is all you have to do. Oh, and this needs to be inside of a process.
Yeah.
The process on clock if rising edge.
Well, I put the type states and the signal in the architecture of the state machine. Like, I said,
Yeah,
architecture
so-
of state machine is. And this is in the same kind of area, the components, and all that. It's not after the begin.
So this book has a pretty good example. Architecture is type state type is, and it gives the values. So like yours, you don't have to do S0, S1, or S2. You could do
You call it whatever you want.
down, up, going down, going up.
Yeah.
Right? Or ready to go down, ready to whatever they are. Yeah, so you give them a name, and then it says signal current state, next state. So this one is done a little bit differently. So it has two processes. One of them updates current state with next state. And one of them is the state logic that says what to do in each of those states. So you can either do it as a single process or dual process. Either is fine.
Okay.
But in either case, you'd have the process. Each clock, this updates the current state. This one then processes on current state or the input. And then this shows you how to implement that case statement.
How do we know here, it says there's a next state, which is just a signal. How do we know what next state is assigned to?
That's what this current state, this is the next state decoder.
Oh, I see.
So in here, this updates what next state will
So
be.
that's more strictly based off of the diagram that we had, kind of.
Yeah. And I usually do single process like this rather than dual process, but either is equally fine.
Okay. Cool. Well, that helps.
Yeah.
Thanks.